13th International Physics Olympiad, year 1962, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com and the Skype name Eduard F1996. Problem number 2. Oscillating cold hanger. A suitable made wire cold hanger can perform small amplitude oscillations in the plane of the figure around the equilibrium position shown. In positions A and B, the long side is horizontal. The other sides have equal length. The period of oscillation is the same in all cases. What is the location of center of mass, and how long is the period? The figure does not contain any information beyond the dimensions given. Nothing is known. It means concerning the detailed distribution of mass. Solution for problem number 2. According to the picture, we have two equilibrium points, this one and this one. It means that the center of mass or center of gravity lie on this line between this point and this point, and suppose that center of mass has a distance x from base of this hanger. Now suppose that d is length of this base of this hanger, which is 42 centimeters. L is the height, which is 10 centimeters. X is the distance from center of mass to the middle of this base. And because we have oscillation in the plane of this hanger, we can count that moment of inertia around this center of mass is ma0 square, where a is some kind of characteristic of a geometrical sizes of this hanger. Now let's count what is the period for all three positions. Due to parallel access theorem, we have these three expressions for all three periods. First case, it's oscillation around this position. L minus x, it's oscillation around this position. And y is oscillation around this position. And all these periods must be equal to each other. Let's talk about first and the second case, where T1 equal T2. It means that we can equalize expressions under the roots, which is this one, and after some calculations we have this expression. So for this expression we have two solutions. One solution is when x equal L over 2, and it's situated exactly between 2 points of oscillations. In that case, A0 could be any, because we have same distance from the center of mass. Other solution is when A0 square equals this one, and x could be in any point between base and the top of this hanger. Let's talk about the second case. As we mentioned, in second case we have A0 square equal x multiplied by L minus x, and after putting into the first equation we will get period equal to pi multiplied by L over g. Let's compare it to the third case. In the third case we have T3 equal this expression, and after some simplification we can get that this T3 greater than this expression, and because y greater than d over 2, that will be greater than L. It means that T3 must be greater than T1. It means that the second solution is not solution. Let's investigate first case when x equals L over 2. It means that y now equal to this expression, and after equalizing T1 to T3 we will get this equation, and after simplification, because y is not equal to L over 2, we have a0 square equals 1/2 yl. Now we have total expression for a0 square. Let's count what is the period in that case. We can count what is this expression when we, instead of a0 square, put 1/2 yl, and finally we will get this expression, 2 pi multiplied by square root from y plus L over 2 divided by g. Let's count what is the period in third case. That will be this expression, and after simplification we have the same result as in the first and second case. Now we just need to put numbers and get what is a total period. After putting all numbers we have this expression, which is 1.03 seconds. That was solution for problem number 2.